Hello mathematicians, we're now going to have a look at volumes. So we really build upon what you did in the Extension 1 course. So you'll remember there that we had a formula for the volume when we rotate a surface of revolution, in other words a curve. We rotate that around either the x-axis, in which case we want pi times the function of x all squared, so this is y equals f of x, y squared is what we want. Or if we rotate around the y-axis, then it will be f of y, which is f of y all squared, which is x squared. However, we're just going to generalize that method here. So we're going to look at deriving volumes as the infinite sum of a series of slices or shells. And with our volumes by slicing, we've got a few methods few sub-methods that we look at. The first one is slices with a circular cross-section, or the disk method. Now this is essentially what you did in Extension 1, perhaps without realizing it, or perhaps it was explained to you. But we're just going to build upon that, and then we're going to expand out, look at other options. The basis of our disk method is to imagine taking an infinite sum of a thin slice of a circular cross-section, in other words, that will be a disk, where we rotate thin strips perpendicular to the axis of revolution. So we imagine, for example, that our area to be rotated is sliced up into thin strips. Those strips are rotated about the axis of revolution, which in this example is the x-axis, and we form, therefore, a series of thin disks. Each of these thin disks then has a volume, which is given by the area of the face, which is the area of a circle, times the thickness of the disk. And the volume then is the expression of summing the total volume is the expression of summing those small volumes over the appropriate range. You should start to have a familiar ring about it now. So the total volume is the sum, this thing here, of n of these disks, each of area given by pi r squared, each of thickness delta x. And essentially, we want to make those disks thinner and thinner, so we want n to become infinite. So it's the limit to infinity of this sum, and that is, as you might remember from the fundamental theorem of calculus, not the fundamental theorem of calculus, from the definition of definition of integration, that is the integral from a to b of a of x dx. Now, I'm going to take a few of your suggestions on board. I'm going to try to speed things up by and also provide you with the worked solutions here. So let's look at this. Show that the volume of a sphere of radius r is that. So first thing is start with your sketch. So on my sketch here, we know that we get the sphere by effectively rotating a circle around either the x or the y-axis. I'm going to choose to rotate it around the x-axis. And on my diagram here, I need to know the formula for the curve that I'm rotating. It's x squared plus y squared equals r squared. And then, using the basically the Extension 1 concept, I'm going to say that the volume is pi outside of the integral from this spot to this spot, minus r to plus r, of y squared, because I'm rotating around the x-axis. And so if I make y the subject of this, it gives me that, which of course simplifies to be that. I can then simply do the integral, so that's no problem to do the integration. Don't lose the pi. Plug in the limits of integration into our expression, carefully trace through, and when we do that after plugging in, we get that the volume is pi r cubed, on 3, which we know is the volume. A, because we were given to it, B, because we should know it in any case. Now our next example could also be an extension 1 question. So I've just got this curve, y equals cos x. We're going from 0 to pi on 2, so draw yourself a picture. This is what the curve looks like. It's going around the x-axis, so we'll have an integral pi and dx. And of course the reason this pi is here in extension 1 is because pi times r squared, where r is the y value, is the area of the disk. The area of the face of the disk at least. So we want cos squared. Now we then know, or you probably know, but I have to rederive, the relationship between cos 2x, the double angle, and cos squared. So we do that rearrangement, do the integral, which is then just a basic integral, substitute in our limits of 0 and pi on 2, all very carefully, and we get pi on 4 as the volume generated. Okay, on our next one we're starting to up the difficulty just a little bit. So we want the volume generated when the area bounded by this curve, so that's our parabola just here, our horizontal line y equals 2, and the vertical line, the y-axis, x equals 0. So it's this shaded area in here. So when that is rotated, first of all, around the y-axis. So if we think about this one, I'm first of all going to be more explicit about how it is a disk method rather than just relying on our extension 1 formula. So I'm going to say, what is the radius of the strip that we're rotating around the axis? So that's the bit in blue just here. That's the radius. So I want pi times the integral, and I'm not now talking about anything except the square of the radius. And it's going around the y-axis, so it's dy, so my limits are also y values, 0 and 2. And then I want to write y in terms, I want to write r in terms of y because I'm integrating dy, so I need my function in terms of y. So r is going to be x squared, and x squared is going to equal y. So my integral is this, which is where we would have got to just using extension 1 methods. Then we do the integral, which is nice and straightforward, and get 2 pi as our answer. Now, next step down, where we're going to be integrating around by rotating around the line y equals 2 rather than the x-axis, we have to be much more explicit about our method. So I want, again, pi r squared to give me the area of the disk formed by rotating the strip. But what's the radius of the strip? Well, when I come to my diagram here, the length of this red arrow is the radius of the strip. And what is the length of that red arrow? Well, it's equal to the difference in distance between the ordinate, which will be x squared, and 2. So it's 2 minus x squared. So this is probably where the thinking comes in for this one. So r is 2 minus x squared. We're going around effectively something aligned with the x-axis, so it's an integral dx. So I need r to be in terms of x. My limits of integration from 0 to pi on 2 are literally from the x value of 0 to the x value of pi on 2. So now my integral becomes pi outside of the integral from 2 to 0 of r squared, which is 2 minus x squared, all squared, dx. After that, it's all okay. So I just expand this out, do my integral, be really careful with all the surds, and I get to this messy thing down here, 32 root 2 pi on 15, and of course it's a volume, so it's units cubed. The next example could be straight from an extension 1 paper, an enclosed region in here. So find the volume of the resulting solid. So in terms of the strip, if I want to phrase it in terms of pi r squared minus another r squared, to get the length of the strip, it's pi times x squared. So that's this, it's hard to write with this thing. That's the y equals x, so it's that x being squared minus this radius, which is x squared, the lower curve squared. So you would have done that in extension 1, but you would have just said one function minus the other and each of them squared. Remember, it's not one minus the other and all squared, it's one function squared minus the other function squared. And that's because it's one radius squared minus the other radius squared. We'll see that what we've done here is really something called the washer method, when we have a look at that later on. The only difference being that it's a disk with a hole in it. So we just go through all of this, and I'm sure you wouldn't have any problem getting to there.